Today's going to be the last lecture on linear power amplifier classes. And in this lecture, we will talk about first class C power amplifier. That means first we will try to find the drain efficiency of class C. And then we will talk about class AB. And in fact, for class C and for class AB, we know that there is a range of conduction angle. And so there are infinitely many possible conduction angle for which one can design the power amplifier. And that is why we will see that the result of class C will be directly usable for class AB also. So as was pointed out, the circuit for class C also is similar to that of the class B. So only difference between this circuit and class B or A is in terms of the DC voltage at the gate. Okay, so we know that for class C, we try to keep the MOS on for duration less than half of the cycle. That means it conducts for angle less than pi. So that is why in this case, we will have to put a negative gate to source DC bias voltage. So in this case, the total input in is going to be minus VGS, DC negative voltage, plus our time varying input. And time varying input we have been taking like this, where theta is omega t. And for this case also, we will assume VTH for the MOS to be 0. So in this case, what we find is that total gate to source, so this can also be called total gate to source time varying, is greater than 0 for duration, say minus phi to phi, and where phi is going to be less than pi by 2. That means it is going to be switched on only for half of the cycle. So now we can plot what will be the input and then resulting drain current. So this is our 0 line. So in this case, our the DC is here. This is minus VGS. So now my input is going to oscillate about this line. So what we find here is that this input is now greater than 0 only for this portion. And this portion you can see is smaller than pi. this is class C input. Now, since the MOS is on only for this much duration, so we are going to get drain current only for this portion, and for the rest of the portion, there will be no current, no drain current. So no drain current portion is going to be from here to this much portion and here. So ID is going to be 0 for this portion. So now we can plot the ID because our objective is to find out the efficiency, and for that we need to find out the output power. For that we need to find out what is the sinusoidal current that is flowing through load, and that sinusoidal current is going to be the fundamental component of the collector, the drain current. So we find that it is non-zero over only this much portion. So starting from minus phi to phi, it is non-zero. And here we have 1 cycle. So for efficiency, we have to find out P load, PDC, and P load is going to be the fundamental current flowing through the load, and this I1 is fundamental of drain current, total drain current. And PDC is going to be, because drain voltage here, DC is VDD always, and there is going to be IDC, and this IDC is also going to be the DC of total drain current, like this was for the fundamental. So let us say that the peak of this drain current is IP. So PDC is VDD into IDC, and IDC is the DC of the drain current. So we have to carry out the Fourier analysis to find out these two components. But before we carry out the Fourier analysis of ID, we first need to know the mathematical expression for this drain current. So we know that in general, this ID is going to be IDC plus fundamental plus other higher components. So we have to first write the mathematical expression for this drain current, which is for simplification purpose will be assumed to be part of cosine. So we will making another assumption that this is cosine nature. And this will be true only if we are assuming the MOS to be linear, which we know that will not be completely true when MOS is driven by large input voltage. but we are going to carry out this analysis so that we arrive at certain result. So this ID is assumed to be part of a cosine function. So ID theta, we know is 0 for theta between phi and 2 pi minus phi, and it is a cosine, and we have assumed the peak to be IP cos theta. So this is the scenario between minus phi and phi. So this is part of cosine function. But here, whatever expression that we have written here, if you plot, then there will be discontinuity at this boundary between 0 and the cosine nature. Because here you can see that.
Sir, I have one doubt.
Yes.
Shouldn't it be 0 for pi to 2 pi minus 2 pi? How did you get 2 pi minus pi? Can you explain that again?
Yes. See, here you can see that the drain current is non-zero from minus phi to phi. And we know that period is always equal to 2 pi. So if you start counting from here, then you have to take a range equal to 2 pi. Total range has to be 2 pi. So if the starting point is at phi, the other point has to be 2 pi minus phi, so that the difference of this and this point is equal to 2 pi. Right?
Okay, got it, sir. Thank you.
So this is how we have labeled the one cycle of the drain current. And since this is periodic, so you can start the starting point from anywhere and then in the point at 2 pi distance from that chosen starting point. Okay, so what I was pointing out is that we have written this expression for the drain current, but there is an issue here because at the phi location here, these two values, they do not agree because cos phi is not going to be 0, which is the function value for the second part, unless phi is pi by 2. That becomes the class B operation. But we are discussing a phi less than pi by 2, so that this is class C. So what we see here is that IP cos phi is not 0, and the second part says that at phi, at this theta is equal to phi, it should be 0. So if you plot this one, what we have just written, then its a plot is going to be something like this, that there will be jump equal to IP cos phi, and then we will have cosine function. So what we have just now written is going to give rise to this kind of waveform, not what we wanted. So here you can see that there is a no jump, right? Non-zero part and zero part both are equal. So this is happening because as was pointed out, ID at phi is equal to this function, which is in general not 0, except for phi is equal to pi by 2. So we have to subtract this much portion from this expression so that ID becomes 0 at minus phi and phi. So therefore, we will have to modify the drain current in this way. IP cos theta minus cos phi for theta between minus phi and phi. So now here you can see that if you put theta is equal to phi, this part is going to be 0. So we are going to get this kind of waveform, 0 at the boundary of the two regions, conducting and non-conducting region. So now in this case, this waveform will shift down by this much amount, and that is what we have done here. And of course, 0 for the remaining portion. But now there is another issue, and the issue is value of the drain current at theta is equal to 0. Now if you put theta is equal to 0, what we are going to get is IP1, this cos theta becomes 1 minus cos phi, right? And look, what we have done is we have assumed that at 0, the value is equal to IP. But now what we find is value is not IP because it is 1 minus, because we added this factor. So it has become less than IP. So now this is not equal to IP. So this modification in the previous step has altered the peak value of the cosine function or the drain current at theta is equal to 0. So now we have to modify this expression so that the peak value becomes IP. So here we see that the new drain current value at theta is equal to 0 is, you can say, more by this factor. So now to regain the amplitude for this drain current to be IP, we have to divide this expression by this factor. So now we get the new expression for drain current as IP cos theta minus cos phi, now divided by 1 minus cos phi. So this is the amount by which the peak has become excess. So we are dividing it to cancel out the effect. And of course 0 for the remaining region. So now let us see whether this expression is okay. So here if we write ID 0, then you can see that this cos theta will become 1, and we will have 1 minus cos phi in numerator, and we have 1 minus cos phi in denominator. So peak value turns out to be IP, and that is what we had labeled. And then value at ID phi is going to be 0 if you put phi here in this expression. So we see that now we have the correct expression for the drain current. So once we have written the correct expression, we can proceed to find out the DC and the fundamental part, because they will be required in finding the drain efficiency. So first we will try to find out the DC part. So what we have to do, we have to find out the average value. DC is basically the average value of the drain current. So we have to take the average of drain current over one cycle. So this will give rise to DC component. So we are carrying out this integration for the Fourier component equation that we had written here. Here, this equation 1. So if you take average, then only the DC component will survive. So, and now we know that drain current is non-zero only over minus phi to phi region. So this integration gets reduced to this range. And here we have IP cos theta minus cos phi divided by 1 minus cos phi d theta. And this will be 2 pi IDC. So if one carries out this analysis, we will arrive at expression for the DC part as IP by 2 pi to sine phi minus 2 phi cos phi divided by 1 minus cos phi. So this is the DC component that will be required for finding out the DC power consumed by the MOS. Now for finding the fundamental, so what we do, we take the equation 1, multiply it by cos theta and integrate over 1 cycle, which is from minus phi to 2 pi minus phi. So if we do this, on the left side, we get this expression. On the right hand side, only the fundamental will survive. Rest all will become 0. And here also the integration range gets reduced from minus phi to phi. So if we solve this, we will get fundamental as so here we have the two important components, but one can try to find out the other higher order components. Say, for example, if we want to know the coefficient of IN, so for that case, we have to multiply equation 1 both sides by cos and theta and carry out the integration. So final integration that we will have to handle is this one. So here, if we carry out this integration and extract the value of IN, the amplitude of the nth order harmonic, then this is what we will get. So keep in mind that although we are carrying out this analysis for so-called class C, all these results are very general and applicable even for class B and A, which we have already studied. Yeah. And will be of course starting from 2, 3, 4, and so on so forth. So here just to check, we can take pi is equal to pi by 2. That means conduction angle is pi. That means we are basically now talking about class B. So for class B, we saw that only the fundamental exist. The first odd harmonic, rest all harmonics are odd harmonics are 0. So here we can see from the previous equation, this equation that cos phi is going to be 0 because phi is pi by 2. Similarly, cos and phi, which appears here, is also going to be 0. So we see that both the terms in the numerator, they become 0 for phi. And if n is odd, for n is equal to 3, 5, 7, so on and so forth. So that is why in is going to be 0 for all these n's. And we have already seen that only even harmonics, higher harmonics exist for class B. Okay. So now we have all the coefficients, all the amplitudes for all the harmonics for drain current. So we can proceed to find out the drain efficiency. EDC. So we first find out the power to load, RF power. So this will be square of the fundamental, which will be flowing through the load. And this can also be written in terms of the fundamental voltage across load and the fundamental current divided by 2. Because we know that the fundamental will flow through the load. So we can see the circuit, equivalent circuit for all those harmonics. IDC. So for this, RFC will act as a short circuit and blocking capacitor open. So IDC flows in this way. For the fundamental, RFC acts as open circuit, blocking capacitor acts as short circuit, and parallel LC acts as open circuit because YLC is 0 implies that ZLC is infinite. Of course, this is uh, true for the fundamental, and for the other harmonics, the equivalent circuit. So here we saw that we have inductor, we have capacitor, and we have load, all three connected to ground. So as the frequency of these higher harmonics increases, it is the path through the capacitor which will be offering the least impedance. So all the higher harmonics, it is called IN, they will tend to flow more through capacitor than through inductor, whose impedance will keep on increasing as the frequency increases. And this will, of course, offer a constant impedance, the load, but it will be definitely higher than the impedance offered by the capacitor. So in approximate way, we can say that all the Hare harmonics, they flow in this way. And since the impedance offered by this capacitor is going to be zero for truly speaking only for very high frequency, so their contribution at the drain is going to be almost zero. So this Vn, it is going to be zero. And these assumptions become more and more accurate as the frequency increases for the harmonics. So this is one of the assumptions that we take. Okay, so here we saw that this V1, the voltage that we will see here, is the consequence of I1, the fundamental flowing through the load. So this is going to be minus RL I1. So this relation we are familiar with. And here the DC voltage is of course going to be VDD, equal to the supply voltage. Okay, so these are the two ways in which we can calculate the load power. Now we can calculate the DC power, which is VDD into IDC. And IDC part we have already derived. So this becomes VDD into IP, peak of the drain current, into 2 pi multiplied by 2 sine phi minus 2 phi cos phi divided by 1 minus cos phi. And PL, if we calculate in terms of fundamental voltage and the fundamental current, so this will turn out to be fundamental voltage by 2, and expression for I1 we have already found out. So therefore, the drain efficiency is equal to V1 divided by 2 VDD into 2 phi minus sine 2 phi divided by 2 sine phi minus 2 phi cos phi. So what we observe here, like the case of class B and class A, that this efficiency is function of the fundamental voltage, or it can also be written in terms of the fundamental current of the drain current. That means we will have to change the input so that we get the maximum efficiency. Now, if we try to draw these voltage, fundamental drain current voltage and fundamental output voltage, then what we will see here is so fundamental of this ID is going to flow through the load, and that fundamental is going to be a sinusoid. So this will be like this. So this I1 will now flow through RL to give rise to V1. But its polarity is going to be opposite. And this V1, when gets added with the drain DC voltage, will give rise to total drain voltage. So total drain voltage we can plot here. In general, it is going to be like this. So this is the total drain voltage. And this is equal to VDD. And this amplitude is what we are calling V1. So here we can see that V1 can be made equal to VDD. There is still room for the growth, this is small amount. And this growth, it can be made equal to VDD by increasing the input. So when we increase the input, then we get the more drain current. And when we get the more drain current with the larger IP, so now we have IP dash, which is greater than IP. So we are now going to get a larger fundamental. So this larger fundamental, when flows through the load, will give rise to larger voltage swing at the output, and that will finally lead to voltage swing equal to VDD. So by increasing the input, we can increase the drain efficiency. So the V1 max is equal to VDD. So when we try to find out the maximum of this, we take VDD by 2 VDD, and rest factor remains same. But there is a catch here, which I will point out. So this is not straightforward. There is an issue here. Issue is that when we increase the amplitude, the phi, the conduction angle in general, is going to change. Let me first write the complete expression for the maximum drain efficiency. So this is for the class C. Now, what I pointed out, that to increase the efficiency, we just need to increase the input. But problem will come for this conduction angle. Here you can see that when we increase this input, what happened is that this new VI, let us call it VI dash, this VI dash now crosses 0 at this point. So here you can see that when you increase the amplitude of the input in an attempt to maximize the efficiency, you invariably change the phi, the conduction angle. So if you want to keep the conduction angle constant, what we will now have to do is we have to change the DC bias. So we can see it more clearly here. So for example, I have here plotted the two cosine functions. So here we have a cosine of say amplitude equal to 1, and here I have another cosine of amplitude equal to 2. So I increase the amplitude of the input from 1 volts, for example, 1 unit to 2 unit. And this is my VGS for the first case. This is the case 1. So here you can see that what we have is phi was from -1 to 1. So this is 2 phi, minus phi to phi. But when we increase the amplitude and gate to source voltage remains same, so now we see that the uh, total input is non-zero over a wider range compared with the previous case. So here now we have conduction angle which is larger than 2 phi, previous 2 phi. So this is greater than 2 phi. So what we will have to do is we will have to now change the DC. So we will have to bring down this DC so that so here you can see that what we have done now is change the DC. Earlier we had minus VGS, now we have minus VGS dash. So we have brought down the DC at the gate so that the zero crossing even for 2 cos theta is same as that for the cos theta case. So when we try to maximize the efficiency, this is the additional tweaking that we will have to do. Otherwise, this factor will also get modified. This factor. So now we can see that what will be the drain efficiency for various values of phi or the conduction angle 2 phi. So we can tabulate it. So since we are claiming this to be class C, so we will take conduction angle which is less than pi but greater than 0. So we will take say 120 degree. And if we take this, we get efficiency which is 89.68%. And this is, you can recall, greater than that for the class B. Now we can further reduce the conduction angle and let us say that take 90 degree. In that case, this becomes 94.04%, very high. So these are the two for class C case. Now, as was pointed out, this is a general case, and by choosing phi suitable, we can convert it to possibly to class B or class A also. So now let us take conduction angle to be equal to 180 degree. That means we want to see if this works for class B also or not. So if you take 180 degree, this will turn out to be 78.6%, which is that of the class B. And when we take 360 degree, this will turn out to be 50%. That means this is class A. And so these are the class A, B, and C. But what about class AB? So suppose we take angle which is greater than pi, but less than 2 pi. That means between 180 and 360 degree. So if we take conduction angle to be 240 degree, which corresponds to class EB, then in this case the efficiency will turn out to be 66.05. So here we see that we have smallest value for class A, then we have for class AB, then for class B, and then of course for class C. So as the uh, conduction angle decreases, the efficiency increases. So one would be tempted to say that try to make it as small as possible, the conduction angle, so that one gets the as high value of the efficiency. So here we see that when it is decreased, this implies eta d max goes up. So we certainly want to have a very high efficiency, but ultimately we also want a certain amount of power to be delivered to the load also. So the problem here is that you can see that when we try to decrease the conduction angle, so if you try to decrease this conduction angle, then there will be very short duration for which the MOS will conduct, and this amplitude will also start getting reduced. So as Vi is brought down, the IP also comes down. So if you bring down IP, I1 is also going to come down. That means power delivered to the load will also keep on reducing. Sorry, here we are not reducing Vi, rather we are reducing this phi. So when we decrease this phi, that means we are basically pulling down this VGS. So when you pull down VGS, so this is the first thing you will have to do. Second thing that will happen is phi will get reduced. So that will then bring down the IP, the peak of the drain current. So that will then bring down the fundamental current through the load. So of course these are also going to come down, and power delivered to load is going to get reduced. So if you want to deliver certain amount of power, then you see that what you will have to do, you will have to increase the input amplitude. So the problem with these class C is that although it gives rise to more efficiency, but the amount of power delivered gets reduced. And this phenomena or this aspect is conveyed by the output power capability parameter. So the CP, which is defined as the maximum power that gets delivered to the load divided by the maximum swing of the drain voltage and the maximum swing of the drain current. So this basically captures that how good the power amplifier is at delivering the power to the load. So this number should be higher for any given power amplifier. So now let us try to calculate this parameter for class C. So for class C, we have to calculate each of these three parameters appearing in the formula. So here we see that the maximum drain voltage swing that can occur is 2 VDD. This is the maximum voltage that will be experienced by the drain, and this corresponds to maximum efficiency. So all those parameters, they need not be valid simultaneously. So here we can see that the maximum voltage is going to be 2 VDD. So at this moment, MOS is going to experience the maximum voltage stress. And the maximum current stress that MOS will experience is this much, the IP. So the maximum current it has to sustain is IP. The maximum drain voltage that it has to sustain is equal to 2 VDD. So we can now write the value for denominator parameters. So ID max is IP max. And what is PL max? So PL max will be the maximum voltage and we know that V1 max is equal to VDD. So this is the maximum voltage swing that the load can experience, and corresponding to that moment, the load will be getting the maximum power. So PL max is going to be VDD by 2RL. In fact, this parameter is constant for all the classes, whether it is class C, class B, or class A. But only thing is that to achieve this maximum power, you will have to provide a different value of the input. So input is not going to be same for all the 4 classes of the input, although the maximum is going to be same. So keep this distinction in mind. So now we have to find out this one. So here, this we know that the fundamental, which is responsible for the power delivered to the load, is given by IP by 2 pi 2 phi minus sine 2 phi by 1 minus cos phi. So from here we can find out the IP and then find its maximum so that we can find out this parameter. So IP then becomes 2 pi I1 into 1 minus cos phi divided by 2 phi minus sine 2 phi. So we are looking for IP max. So it says that it should be I1 max. And this I1 max leads to maximum voltage swing. So this I1 max gives rise to VDD swing divided by RL. So this IP max becomes 2 pi VDD by RL 1 minus cos phi divided by 2 phi minus 2 phi. So now we have IP max and we have found out VD max and we have PL max. So we can substitute each of these in the definition equation here and carry out the calculation. So if we do all these calculation, CP will turn out to be 2 phi minus sine 2 phi divided by 8 pi 1 minus cos phi. So here, so for class A and for B, both for these classes, we have found this was equal to 1 by 8. That means 0.125. Now we can see this value for other classes. Here. So here we have taken phi on x-axis and we have plotted Cp. So phi corresponding to 2 pi pi, that means this is class A. So 2 phi is equal to 2 pi, and this is class B. So class C region is from 0 to pi by 2, and AB is over this region. So here you can see that for class C, the Cp is less than 0.125. So 0.125 is somewhere here. So this decreases, and in fact it becomes 0 when you take the phi 0, for which case you get the efficiency to be high. So there is a trade-off that one has to do between the power delivered to the load and the efficiency. So based on the application, one has to choose which class of operation one wants. And here's another plot which says that the power delivered to the load is going to decrease with the decrement in the phi. So this is class B, this is class A, this is AB region, and this is C mode of operation. So here we have fundamental I1 current, and this is IDC. So since IDC decreases, so the power consumed obviously decreases. So PDC goes down because as the phi decreases, this IDC is coming down, so PDC is coming down, so efficiency will of course go up. But unfortunately, here we can see that the fundamental is also decreasing. That means PL will also come down. And here we have a plot of efficiency for all the cases, starting from case A, for which we get 50% efficiency, and for conduction to be 0, we get 100% efficiency. But this is of no use because power delivered is also going to be 0 to the load. So this was for class C, and as was pointed out, for class AB, only thing we have to do is change the DC bias. So DC bias now is going to be positive, and now my input will oscillate about this line. So here we see that now conduction angle is more than phi. So this is 2 phi, starting from minus phi, this point going up to phi, and this 2 phi is greater than pi, because pi is from here to here. So this is pi range. So whether we start from this current voltage, input voltage waveform leading to drain current like this, So mathematically, all the steps that we carried out, they're going to be exactly same, and in fact, the same expression will turn out. So whatever result we have got for class C is in fact so general that it applies not only for class C but class AB and class B and A also. And we have seen this thing from the efficiency plot for various values of the conduction angle. And the circuit for class A also, sorry, AB remains exactly same as that of the class C.